the greatest machine humanity has ever built. Armed with thousands of giant magnets, it is colder than space and creates collisions 100,000 times hotter than the center of the Sunday. Its purpose? To test the rules of the universe. And for 50 years, it passed every single test perfectly, until that day, because this giant machine noticed an anomaly in the decay angles of a particle. This was a deviation that should only happen once in 16,000 tries. But this deviation has refused to go away for a decade. Now, 2 separate detectors are reporting the same impossible result. Is the most successful scientific theory we have telling a lie? If this mystery is blowing your mind, like and subscribe, because we're about to dive into the truth behind that lie. Let's begin. For 50 years, the world of science believed in an unshakable truth. There was a rulebook that governed the universe. Its name was the Standard Model, and it was never wrong. It passed every experiment. Every prediction came true. It shrugged off every challenge. Scientists trusted it, the way they trusted gravity, until deep beneath the border of France and Switzerland, a giant 17-mile machine smashed particles millions of times smaller than an atom into each other. Because a whisper emerged from that wreckage, saying everything had changed. It showed that the most reliable map we had ever known might be missing its most important piece. The place this whisper came from is the most mind-boggling machine humanity has ever constructed. Its name is CERN. Imagine a giant circle, stretching for about 100 feet beneath your shoes, crossing an international border. This circle is so large, it extends from Switzerland to France and back again, passing under farms, villages, and the foothills of the Alps. It's a full 17 miles from end to end. If you tried to walk a lap inside, it would take most of your day. That's why the people who work there use bicycles in the tunnel, because this machine takes the smallest parts of the universe, protons, and subjects them to an unbelievable process. A proton is a tiny particle inside an atom, millions of which could fit onto the period at the end of this sentence. CERN takes these particles and accelerates them to near the speed of light, about 670 million miles per hour. At this speed, a single proton circles the 17-mile ring more than 11,000 times per second. But why? Why would you build such a monster? Because this machine's real job is to take 2 beams of these protons and smash them head-on. In that moment of collision, for a fraction of a second, the temperature in that tiny point reaches more than 100,000 times hotter than the center of the Sunday. For that instant, CERN recreates the infancy of the universe, that first moment right after the Big Bang. What scatters from that wreckage are the clues to what everything is made of. And lately, these clues have started to shake the most fundamental pillar of physics. Without understanding that pillar, you can't understand why this whisper is so terrifying. This pillar has a boring name but incredible power. The Standard Model. It's the fundamental ingredient list for everything around you. Just like the periodic table lists the elements, the Standard Model lists the most basic building blocks of the universe. The quarks that make up protons, the electrons that buzz around atoms, particles of light, and their heavier, rarer cousins. The entire menu fits on a chart smaller than a poster on your wall. What makes this model legendary are its prophecies. For 50 years, time and time again, its mathematics predicted the existence of particles that had never been seen. Years, even decades later, when scientists built a machine and ran the experiment, the particle was there, exactly where the rulebook said it would be. It predicted the W and Z particles. They were found. It predicted the top quark. It was found. And in 2012, it made its most famous prediction, the Higgs boson, which had been sought for nearly 50 years. A bullseye. This rulebook passed every test thrown at it. But here's the strange truth that keeps scientists up at night. They already know it's incomplete. The Standard Model says nothing about the gravity holding you in your chair right now. It has no explanation for the invisible dark matter that makes up most of the universe. And most importantly, it can't explain why you, me, and this planet exist at all. So scientists live with a strange feeling. They have the most accurate rulebook in history, and they are certain its pages are missing. This is why CERN exists. It was built to find that crack, that first wrong measurement, the first clue pointing to those missing pages. For years, the machine pushed, and the rulebook held, until scientists looked at the giant cameras that watch those collisions. So how do you take a picture of something smaller than an atom? You can't, but you can follow the tracks it leaves behind. The collision point is surrounded by the most powerful cameras on Earth. These aren't like the camera in your phone. These are machines the size of buildings, weighing thousands of tons. The largest, Atlas, is taller than a 6-story building and as heavy as the Eiffel Tower. Another, CMS, is heavier than more than 30 fully loaded jumbo jets stacked on top of each other. These giants were built to study the smallest things that exist. When a particle flies out of the wreckage, it punches through the detector's layers. Each layer registers a tiny ping. Like a detective following footprints in the snow, scientists connect these pings to track the particle's path, its speed, and most importantly, how much it bends in a magnetic field. That bend is its identity. But there's a problem. The collisions are so fast, the detectors are faced with about 40 million snapshots a second. If you tried to save it all, you'd fill up every hard drive on the planet in minutes. So the vast majority of it is deleted instantly. Only the rare events that look interesting are saved. And that's where a special detector, LHCb, the hero of our story, comes in. It doesn't look for new particles. It watches how known particles fall apart, how they die. It's looking for the slightest difference between what the rulebook predicts and what actually happens. And after watching billions of disintegrations, it found that difference in the most unexpected place. Because some particles are born to die, the instant they appear, they begin to fall apart. Scientists call this process decay. It sounds grim, but it's one of the most important events in physics, and it's happening on a tiny scale, even inside your body right now. The universe is full of stable particles. An electron, for example, can live forever, but many particles are heavy and restless. They carry too much energy to stay put, so the moment they're created, they break down into lighter, calmer pieces. It's like a snowflake landing on warm skin. For a moment it holds its perfect shape, then it transforms into something simpler, water. Most particles have a much shorter lifespan. Some transform in less than a trillionth of a second. You can never watch it happen. You can only study the pieces left behind, and those pieces are everything. Because when a particle decays, the rulebook controls exactly how it can fall apart, what it can turn into, and how often it will choose which path. This is why decays are like a fingerprint. If you watch enough particles fall apart and count how often each pattern emerges, you can test whether the universe is obeying its own rules. The most sensitive of these tests are the rarest decays. Disintegrations that happen once in a million times, or even less, are a true treasure, because it is precisely in these rare events that hidden surprises love to hide. Think of it this way. Imagine a still pond. If you drop a single pebble into it, you'll notice every ripple. But in a stormy sea, that pebble vanishes without a trace. A rare decay is that still pond. If there is an unknown particle lurking in the dark, too heavy for the collider to create directly, it can still reach out like an invisible hand and slightly deflect this fragile process. And we would see those ripples, that deflection. The LHCb team spent years hunting for just such a decay. It was so rare it happened about once in a million times. By accumulating hundreds of billions of collisions, they patiently searched for just a handful of these strange events. And when they finally had enough data, the result refused to match the rulebook. This was the moment the rulebook began to tremble. So what is the name of this rule-bending event? The funny thing is, physicists named one of the strangest events in the universe after a cartoon bird, and the reason is pretty silly. The star of our mystery is a particle called a meson. When the collider smashes protons apart, the debris sometimes forms this heavy little droplet. It contains a rare and heavy building block called a beauty quark. This quark makes the meson special, and it also prepares its end. Because the meson is unstable, it falls apart the moment it is born. Most of the time, it decays in ordinary ways. But once in a million times, it does something much rarer. It breaks apart into 4 smaller particles at the same time. And a physicist looking at the diagram for this decay, on a losing bet in a game of darts in the 1970s, decided the diagram looked like a penguin. it was a joke, but the name stuck. Today, serious scientists at CERN will say penguin decay with a completely straight face. Behind this playful name, however, lies a deadly serious idea. This decay is one of physics's best traps. Because it is so rare and so sensitive, the slightest outside influence will show up glaringly in the results. And so, the LHCb team set this trap. They sifted through an unimaginable mountain of data, about 650 billion B mesons recorded over several years of collisions. From that mountain, they extracted the tiny sprinkle of the rarest decays. They didn't just count how often it happened, they did something clever. They measured exactly how the decay took place, the angles at which the particles flew out, the fine details that the rulebook claimed to predict, down to the last decimal place. And when they compared their measurement to what the standard model demanded, the numbers didn't match. The penguin was misbehaving. There was something in the shape of its disintegration that was deviating from the rules. We now know the basic concepts. There is a giant machine that accelerates the smallest parts of the universe. There is a rulebook that has been correct for 50 years, telling us how everything should work. And now, in a place where that rulebook is most sensitive, in a 1 in a million event, a crack has appeared. A crack seen by 2 different detectors. But this is just the beginning. Now we wonder, what does this crack look like exactly? What are the numbers that are off? What did the scientists see that made them hold their breath? Because the real findings are far more surprising than this theoretical groundwork. And now for the real shock. Because what the scientists found was not just a theoretical deviation, it was a concrete number. A stubborn, unexplainable number that has been growing for a decade. What exactly was wrong? The answer is hidden in a single strange number that has been haunting physics for over a decade. The penguin decay was happening about as often as the rulebook predicted. So at first glance, nothing looked wrong. The problem was hidden in the angles. Think of it this way. When the B meson breaks apart into those 4 pieces, the pieces don't just scatter randomly. They spray out in a specific pattern, like sparks from a firework. And the rulebook claims to know not just how often this event will happen, but the shape of that spray, the precise angles the particles should take as they fly away from the wreckage. Scientists invented a special ruler just to measure this. It was a kind of angle score, designed to cancel out the messy, hard-to-calculate parts, so whatever was left would be a clean, honest test of the rules. The standard model predicts a clear value for this angle score. Nature was supposed to obey, but it didn't. This deviation wasn't new. It first showed its face in 2013. Back then, scientists noticed this angle score drifting away from the rulebook. It was a faint signal. It could easily have been a fluke. They thought more data would erase it, like a silhouette that becomes blurry as you get closer. So they collected more data. The deviation remained. In 2016, they checked again with a bigger pile of collisions. It was still there, in the same direction, about the same size. A signal that refuses to die is either a mistake that no one has found, or it's real. And then came December 2025. The team published their most powerful study yet, with the largest and most carefully cleaned dataset they had ever assembled. Years of work, hundreds of billions of decays, the most sensitive look at this penguin in history. The deviation didn't just survive, it grew. When they combined everything, the difference between the measurement and the rulebook reached a level that scientists call 4 sigma. Think of it as a tug-of-war between 2 numbers. On one side, the prediction, on the other, the measurement, and the rope had just been pulled to its tightest point yet. So what does 4 sigma mean? This one word is the difference between a headline and a yawn, between a real discovery and a ghost that tricked everyone. Sigma is just a fancy word that asks a simple question. How surprised should you be? Flip a coin 10 times. Getting 6 or 7 heads wouldn't surprise you. That's normal luck. But flip it 10 times and get 10 heads, and you'd raise an eyebrow. Flip it 100 times and get 100 heads, and you'd no longer believe the coin was fair. Sigma measures that exact feeling. It tells you how far a result is from boring, ordinary chance. 1 sigma is nothing. 2 sigma is a little interesting. 3 sigma starts to feel weird. But 4 sigma, the level our penguin has reached, is a different beast entirely. At 4 sigma, the odds of the result being a complete fluke of chance drop to about 1 in 16,000. Imagine a stadium with 16,000 people. Only one person in that roaring crowd holds a golden ticket. You reach in blindfolded, pull out a random person, and somehow find that exact ticket holder. That's how unlikely it is that this penguin deviation is a simple accident of chance. This is why when scientists saw 4 sigma, their gut told them something real was happening. The measurement wasn't just hovering near the rulebook and drifting by accident. It was parked stubbornly far away, and chance was almost eliminated as a reason. You'd think that would settle it. 1 in 16,000 sounds like a sure victory. In almost any other field it would be. But particle physics plays by the most ruthless rules in science. In this world, 1 in 16,000 is not a discovery. It's not even close. It's officially still a maybe, a hint that scientists are forbidden to celebrate out loud. This seems like madness. Why throw away such good odds? Because physicists have been tricked before. By signals that look just this convincing, only to vanish into thin air. To officially announce a discovery, physicists demand a level of proof that borders on paranoia. The magic number is 5 sigma. That one step is a giant leap. At 5 sigma, the odds of the result being a random fluke plummet to less than 1 in a million, about 1 in 2 million. Only when a signal climbs that high can scientists stand up and say the word discovery. That's why, even now, the rulebook is technically still standing. The penguin deviation is loud. It's stubborn. It has survived for over a decade, and only gotten stronger. But it hasn't yet broken that 5 sigma wall. So the official story is cautious. The standard model has not fallen, it has only begun to tremble. But there is one more detail in this story that changes everything. You can blame one machine for seeing a ghost, but when 2 rival machines see the same ghost, what do? Because you start to believe in the ghost. And that turned a quiet hint into something much harder to ignore. Remember, the collider doesn't have just one detector watching the collisions. The team hunting the penguin used LHCb, the one specially built to study these sensitive decays. But elsewhere on the same giant ring sits another monster detector, called CMS. This is the giant, heavier than more than 30 loaded jumbo jets stacked together. A different shape, different parts, different software, and run by a completely separate army of scientists who would love nothing more than to prove their rivals wrong. This competition is science's secret weapon, because when 2 rival teams, using 2 different machines, arrive at the same answer, it becomes very, very hard to dismiss the result as a simple mistake. A flaw in one detector will almost never show up in the exact same way in a completely different detector. So scientists waited to see what CMS had to say about this penguin. And CMS found the same thing. When the CMS team measured the same kind of decay, their result deviated from the rulebook in the same direction and by a similar amount. Their measurement wasn't as sharp as LHCb's. Think of it as 2 people describing the same shadowy figure across a field. One has binoculars, the other has their naked eye. The one with binoculars sees more detail, but they are both pointing at the same spot, saying, "Yes, there's something there." 2 machines, 2 teams, 2 completely separate ways of processing the data. And they are both pointing at the same gap, in the same place, in the same direction. This was the moment the story shifted. A lone 4 sigma hint from one detector is something experienced physicists have learned to greet with distrust, because they've been tricked just like that before. But a deviation that shows up in 2 independent machines is a different animal. This is the difference between a single witness and 2. Conferences buzzed, late-night debates happened. Scientists who had spent their entire careers trusting the standard model suddenly had to ask if the missing pages were finally peeking through. And yet, even with the 2 machines in agreement, the smartest people in the room refused to fully celebrate, because one loophole remained. One messy, frustrating possibility that could explain this whole deviation in a boring way, with no new physics at all. It comes from a piece of math so devilishly hard that no one on Earth can calculate it cleanly. If that messy math is hiding a bigger effect than anyone thought, the whole mystery could collapse back into the rulebook, leaving nothing strange behind. and this troublemaker has its own ridiculous nickname. The entire mystery could collapse because of a tiny nuisance that scientists call the charming penguin. The name might sound cute, but the problem behind it is a nightmare. And to understand it, you have to remember why scientists trusted their angle score. They claimed the rulebook predicted that number with razor sharpness. That's why when the measurement came out wrong, it looked like the rulebook was wrong. But there's a catch. To know the exact prediction, you have to do some math. And one part of that math is so brutally difficult that no one on the planet can solve it cleanly. That difficult part involves a particle component called a charm quark. These flickering charm quarks blur the prediction. They add a smudge to the math that scientists can't fully clean off. And because this smudge involves a charm quark sneaking into the penguin decay, physicists smilingly call it the charming penguin. Now you can see the danger. If the effect of those sneaky charm quarks is bigger than scientists think, they could be knocking the angle score off kilter all by themselves. No new particles, no missing pages, no revolution, just a known part of the rulebook that no one could calculate well enough. The entire exciting deviation could be ordinary physics in disguise. So, how big is the effect of the charming penguin? That's the million-dollar question, and the honest answer is that no one is completely sure. The best calculations scientists can do suggest the charm quark smudge is too small to explain the whole deviation, which points to something genuinely new. But there's a humbling problem. The math is so messy that the scientists can't fully trust their own answers. This is the loophole that keeps the rulebook alive. As long as scientists can't rule out a fat, charming penguin, they can't be sure the deviation is new physics. The boring explanation refuses to die completely. So what do we do now? We have a crack seen by two machines on one side, and a math problem no one can solve on the other. How do scientists deal with this dilemma, and what steps are they taking to find the truth? So how do you deal with this dilemma, and stubborn signal seen by two machines on one side, and a math problem no one can solve on the other? The answer is hidden in the most disciplined, most paranoid corner of science. Scientists refuse to celebrate because they've seen this movie before. What makes them so cautious? What makes them demand such a high standard of proof? Are the ghosts of the past. And there's one story that haunts every physicist studying this penguin. A signal that looked even stronger than this one. A discovery that had hundreds of scientists racing to explain it. And then, almost overnight, it vanished, as if it had never been there at all. Let's now descend into the story of this ghost, this cautionary tale, because you need to understand how far science will go to not fool itself. This happened around 2015. Two of CERN's giant detectors, working separately, noticed something strange in their collisions. When certain collisions produced a pair of light particles, an unusual number of those pairs carried roughly the same heavy weight, a value around 750 on the scale physicists use. A small pile-up of events in a place where the rulebook predicted nothing special. A bump like this is a dream come true. It's the classic fingerprint of something brand new, a heavy, unknown entity briefly popping into existence and then decaying into that specific pair. And the thrilling part was that two different detectors, run by rival teams, both saw the same bump at the same spot. The very thing that makes a signal hard to ignore. The same thing that's happening with our penguin today. The physics world caught fire. Scientists looked at the bump, did some quick math, and realized it was about 3 to 4 sigma strong. Strong enough to make hearts race. Strong enough to feel real. And so, the gold rush began. In just a few months, scientists wrote nearly 500 papers trying to explain the bump. 500. Researchers around the world worked late into the night, spinning theories about what this new particle could be, what secrets it could unlock, how it could completely break the rulebook. Everyone wanted to be the first to name the discovery of the century. But then more data came in. The collider kept running, kept collecting collisions. Scientists loaded the fresh data into the same analysis, their eyes locked on that magic spot around 750. They were expecting the bump to grow even taller, to smash through the 5 sigma wall into victory. The bump got smaller, then it got flatter. Then, as if someone had quietly erased it, it was gone. It had all been a fluke. a random pile-up of ordinary events that had conspired to fool everyone. The kind of accident that statistics warns can secretly emerge when you check enough numbers. 500 papers written about a particle that never existed. The bump was a ghost, and it evaporated the moment the light got brighter. This wasn't the first time either. Years earlier, another CERN machine had seen a particle hint that climbed toward 4 sigma and then melted away with more data. Another lab had once seen a signal that screamed even louder, and it too had vanished into nothing. Again and again, beautiful results have seduced clever people, only to disappear like a mirage on a hot road. This history is the cold water every physicist keeps close by. It's why they refuse to pop the champagne over our penguin, no matter how stubborn the deviation seems, no matter how many machines agree, because they've been burned. They remember the 750 ghost. They know that chance can wear a very convincing mask. This is why the team studying the penguin holds the line. They say maybe. They say promising. They say the evidence is accumulating. But they do not say discovery, because they refuse to be fooled a second time. And yet, if the penguin deviation is real, if it survives the next flood of data, it raises the most exciting question in this story. What exactly is pulling it? What invisible thing could be reaching into a decay and bending the rules of reality? If this deviation is real, then something invisible is reaching into that decay and pulling it off course. And whatever that thing is, the collider can't see it directly. This seems impossible. How do you detect a particle that the machine is not powerful enough to create? The answer is one of science's cleverest tricks, and it works like a detective solving a crime no one witnessed. Imagine a still room where a door slowly swings open by itself. You never see a hand, you never hear a footstep, but the door moved, so something must have pushed it. By studying exactly how it swung, how fast, how far, in which direction, you can learn a surprising amount about the invisible thing that pushed it, even though it remains completely out of sight. This is the entire idea behind the penguin. A rare decay is supposed to fall apart in a precise way. If a hidden particle exists, even one too heavy for the collider to build, it can, for the tiniest moment, enter the process and bend the outcome. We never see the particle, we only see the bend. The crooked angle is the swinging door. This trick has solved huge mysteries before. Over 100 years ago, scientists studied a strange type of radioactivity, the way certain atoms quietly fell apart. They could measure it, but they didn't know what was causing it. The particle actually responsible remained hidden for about 80 years, until a powerful enough machine could finally create it and confirm it was there. The hint came first, the proof came lifetimes later. So what could be pulling our penguin? Scientists have a few suspects, and they are all wild. One idea is a whole new force of nature. You already know a handful of forces. This new force could lean on the penguin just enough to bend it. Another suspect is a strange new particle that does something no known particle can. It would act like a bridge, connecting 2 families of particles that the rulebook keeps strictly separate. If a particle like that exists, it could quietly carry influence across that hidden corridor and reshape the decay. If any of these suspects are real, it would be the first crack in the most successful rulebook in history, the first definitive proof that the standard model has missing pages, the first time in 50 years that physics has gotten a peek at something truly beyond the map. Entire new chapters of science would open up. This is why the stakes feel almost unreal. A crooked angle in a 1 in a million decay could be the loose thread that unravels our entire picture of reality. But the penguin is only one of CERN's mysteries, and to feel the full weight of what this machine has found, you have to go back to its most famous victory, a particle hunted for nearly 50 years, a particle that explains something strange about your own body right now, because there is a particle that decides how heavy you are, and scientists chased it for almost 50 years before they finally caught it. Its name is the Higgs, and to understand why it matters, you have to ask a question that seems almost too simple. Why does anything have weight? Why is a bowling ball heavy and a feather light? Why does a planet pull harder than a pebble? The deep answer is far stranger than you might guess. In the 1960s, a quiet scientist named Peter Higgs proposed a strange idea. He suggested that all of space, every inch of it, is secretly filled with an invisible field. Not air, not light, something much stranger, woven into the fabric of the void itself. And as particles move through this hidden field, the field exerts a drag on them. That drag is what we feel as mass. Imagine you're walking through a room. Easy. Now, imagine you're walking through a swimming pool. The water clings to you, slows you down, makes every step feel heavy. The Higgs field works a bit like that pool, except it fills the entire universe. Some particles barely feel it at all and pass through almost untouched, remaining light. Others are gripped tightly, becoming heavy. How much each particle interacts with the field determines its weight. This idea was beautiful, and for decades, it was just an idea. To prove the field was real, scientists had to find its matching particle, a ripple in that invisible pool. They called it the Higgs particle. The problem was, this particle was heavy, shy, and fell apart almost instantly. Catching it would require a machine far more powerful than anything that existed. That machine became the Large Hadron Collider. Finding the Higgs was one of the main reasons it was built in the first place. For years, the giant detectors smashed protons together and sifted through the debris, searching for the faint fingerprint of a particle that vanished the instant it was born, and in 2012 they found it. The crowd at CERN erupted in cheers. Peter Higgs, an old man by then, sat in the audience, wiping away tears as scientists confirmed the particle he had dreamed up half a century before. It was one of the greatest triumphs in the history of science. The rulebook had made a bold promise, and the universe had delivered. Now, here's why this directly affects you. Without the Higgs field, particles would have no mass. With no mass, they would all zip around at the speed of light, never slowing down, never clumping together. Atoms could not form. Without atoms, there would be no molecules, no water, no rock, no air, no cells, no you. The very fact that you are sitting here, made of solid matter, is because that invisible field is gripping the particles in your body, giving them weight. So the Higgs isn't a distant curiosity. It's the reason you have a body. It's the reason the universe is filled with stuff, instead of just a blur of racing light. And finding it proves something powerful. When the rulebook makes a wild prediction, it's usually right, which makes it even harder to dismiss the penguin deviation. The same kind of physics that found the Higgs with bullseye accuracy is now whispering that something is wrong. But the Higgs explains how you have a body. It doesn't explain a much deeper puzzle. Why is there anything to weigh in the first place? Because according to every rule scientists know, you shouldn't exist. Neither should the stars, or the planets, or a single speck of dust. The universe should be empty. This is one of the greatest unsolved mysteries in all of science, and it starts the possible moment the universe was born. Rewind to the Big Bang, that colossal burst of energy that started everything. In that first searing moment, the universe was nothing but pure energy. And one of the most solid rules in physics says that when energy turns into matter, it never just makes one thing. It always makes a matching pair. Every time a particle of matter pops into existence, a mirror version appears beside it. Scientists call that mirror version antimatter. For every speck of matter, an equal speck of antimatter. They are born together at the same time. The two are perfect opposites. They are created in the exact same amounts, one for one, every single time. The math is strict. Matter and antimatter must always be in perfect balance. Now, here comes the fatal part. When a piece of matter meets its antimatter twin, they don't bounce, they don't stick, they completely annihilate each other, vanishing in a pure burst of energy. Nothing solid is left, just a flash of light where two particles used to be. So follow the logic to its brutal conclusion. The Big Bang should have made matter and antimatter in perfectly equal amounts. Then, as the young universe cooled and became crowded, every particle of matter should have run into a particle of antimatter and been annihilated. Every single one. The entire universe should have annihilated itself in its first moments, leaving behind only a sea of light expanding into endless empty space. No galaxies, no sun, no Earth, no life. Just a cold, glowing void where a universe was supposed to be. But look around you. Matter obviously survived. The stars are burning, the oceans are full, your heart is beating. The universe is filled with the very solid stuff that should have been annihilated at the dawn of time. Somehow, matter survived the death sentence. It escaped that great annihilation and went on to build everything you've ever seen. That escape is the mystery. And now for the miracle. Because there was only one way out of this trap. The Big Bang could not have been perfectly balanced after all. Somewhere, somehow, a tiny bit more matter must have been created than antimatter. A microscopic surplus. A slight tilt in the scales. How small? Scientists believe that for every 1 billion antimatter particles, there were about 1,000,000,001 matter particles. Almost everything was annihilated. Billions of pairs wiped each other out in flashes of light. And from every round of destruction, just one lonely matter particle survived. Those lone survivors are everything. Every atom in your body, every star in the sky, is built from the rare leftovers of a battle that nearly emptied the universe. You are made of the 1 in a billion survivor. But this raises a furious question. What gave matter that advantage? What tilted the scales in its favor? And could CERN catch the universe in the act of cheating? Right now. That's why, to explain your own existence, scientists had to catch the universe playing favorites. And in 2025, the collider finally caught it red-handed. Remember the puzzle. The Big Bang should have made matter and antimatter in perfectly equal amounts. And they should have annihilated each other into nothing. For the universe to survive, something had to break the balance. Matter needed a secret advantage over antimatter, even a microscopic one to leave behind the leftovers that formed everything. So scientists went looking for that. Or, if you look closely enough, does one behave just a little differently than the other? If the two were truly identical in every way, the universe would have cancelled itself out, so the survival of everything depends on a tiny flaw in the mirror. Physicists have a name for that flaw. They call it symmetry violation, which is a fancy way of saying the mirror is slightly cracked, and matter and antimatter don't perfectly match. Scientists had noticed hints of this crack before, decades ago, but only in a narrow family of particles. They could never tell if the same flaw showed up in the ordinary, everyday building blocks that make up protons and neutrons, the actual stuff of your body. And those building blocks were the ones that mattered, because the universe was made of them. So the team running LHCb went looking. They studied a heavy, short-lived cousin of the particles inside you, a heavy droplet made of 3 of the same basic components found in every proton. They tracked how this particle fell apart. Then they tracked how its antimatter twin fell apart. If matter and antimatter were perfect mirrors, the two should have decayed in the exact same way, at the exact same rate. But they didn't. The team sifted through years of collisions, comparing the particle to its antimatter twin over and over, and a gap emerged. The matter version and the antimatter version decayed at slightly different rates. The mirror was cracked. For the first time in history, scientists watched this everyday class of matter and its antimatter counterpart behave differently, with enough certainty to call it a true discovery. This was a genuine first. The crack in the mirror was finally caught in the kind of particle that builds the visible universe, the family that includes the protons and neutrons in every atom in your body. It was the strongest sign yet that nature really does play favorites, leaning slightly toward matter. And yet, even this triumph carried a frustrating surprise. The scientists measured the crack. They confirmed it was real. But when they checked how big it was, the crack was far too small to explain the entire survival story of the universe. The tiny advantage it gave matter was real, but it wasn't nearly enough to account for the flood of all the matter we see around us. So the deepest part of the mystery is still wide open. The universe clearly survived its death sentence. Scientists have now caught it bending one rule, but the bend is too gentle to have finished the job. Something bigger, still hidden, must have given matter a much stronger push. That hunt leads directly to the strangest kind of matter humans have ever made, a type of matter so dangerous and so rare that CERN builds it one fragile speck at a time. And that matter was used to answer one of the most fundamental questions humanity has ever known. If you drop antimatter, which way does it fall? Down or up? For decades, no one knew. And the question was so wild, it sounded like science fiction. Think how strange this is. You've dropped thousands of things in your life. A phone, a spoon, a ball. A phone, a ball. Every single one fell down, pulled by gravity toward the floor. It feels like the most obvious rule in the universe. But antimatter is the exact opposite of matter in so many ways. Its charge is reversed. Its nature is reversed. So scientists had to ask an honest question. What if its gravity is reversed too? What if, when you let go of an atom of antimatter, it floated upward instead of falling down? What if there was such a thing as anti-gravity, and antimatter was the key to it? This was a real scientific question, debated seriously for decades. If antimatter fell up, it would shatter our understanding of gravity, breaking one of the biggest theories in all of science. It might even give a clue as to why antimatter is so scarce. Maybe it was just repelled by everything, pushed away into the void. The idea was thrilling, but it was also completely untested, because no one had ever managed to just drop antimatter and watch. The problem was always the same. To watch something fall under gravity, you have to hold it gently and then let it go. And gravity is an incredibly weak force. A magnet on your fridge easily beats the gravity of the entire planet on a paperclip, so powerful magnetic forces were completely overwhelming the weak pull of gravity. The solution required patience and courage. Scientists built a tall, vertical trap and filled it with anti-hydrogen atoms, held in place by a magnetic grip. Then they did the scary part. They slowly, carefully weakened the magnetic walls at the top and bottom of the trap, turning down the force bit by bit. As the magnetic grip weakened, the only thing left to guide the atoms would be gravity itself. The question was simple. As the atoms escaped, would more of them pop out the top or fall out the bottom? They ran the experiment, weakened the trap, and watched where the anti-hydrogen atoms went as they escaped and annihilated on the walls. About 8 out of every 10 atoms went down. Antimatter fell. It fell toward the ground. The same way your phone falls. The same way everything has always fallen. There was no anti-gravity, no upward floating, no reversed pull. When you drop antimatter, it obeys gravity just like the matter in your own body. This settled a question that had been hanging in the air for almost 100 years. Antimatter falls down. This closed one door on the mystery of the missing antimatter. Whatever wiped almost all the antimatter from the universe, it wasn't some strange reversed gravity. The question of why matter won remains wide open, with just one wild idea crossed off the list. But all of these experiments keep coming back to one place, one focal point, that penguin decay. And at the heart of that decay is a particle that shows up again and again at the center of CERN's strangest puzzles. And that particle keeps acting like it's hiding a secret. Its name is the muon. It is raining down on your head right now, passing right through your body. This particle, which you met briefly inside the penguin decay, is the electron's big cousin. It behaves like a normal electron in almost every way, except it's roughly 200 times heavier. Think of an electron that went to the gym and got massively jacked. The same basic personality, with a lot more weight behind it. Muons are everywhere, even though you never feel them. High above your head, particles from deep space are constantly slamming into the top of the atmosphere. These collisions spray showers of muons that rain down toward the ground at nearly the speed of light. Right now, a few are passing through your body every second. They slide harmlessly through your skin, your bones, and the floor beneath you without a trace. They are ghost-like, coming and going before you can even notice. But the muon has a dramatic quirk. It doesn't last. A muon only survives for about 2/millionths of a second before it decays into lighter particles. Blink, and you've missed the lifetimes of countless muons. It's this fleeting existence that makes scientists love to study them. They are born, live their momentary lives, and decay in a way that the rulebook claims to predict perfectly. Here is where things get interesting. Scientists have a deep belief about the electron and its heavier cousins. They believe these particles should be treated exactly the same by the laws of nature, identical in every way except for their weight. The fancy way of saying this is that the different cousins should be perfectly balanced. An electron and a muon should act like the same particle wearing different sized jackets. But the muon keeps misbehaving. Over the years, the muon has shown up at the center of several of physics's biggest puzzles. Experiments keep finding small hints that the muon isn't behaving exactly as the rulebook demands. It wobbles where it should be steady. It tilts where it should be balanced. None of these hints have ever been strong enough to count as proof on their own, and some have vanished with more data. But the pattern is hard to ignore. Over and over, when something looks strange in the deepest experiments, the muon is somehow involved. And remember our penguin. When that meson fell apart in its strange rule-bending way, 2 of the particles it produced were muons. The muon sits at the very heart of the decay that started this whole mystery. Building blocks were the ones that mattered, because the universe was made of them. So the team running LHCb went looking. They studied a heavy, short-lived cousin of the particles inside you, a heavy droplet made of 3 of the same basic components found in every proton. They tracked how this particle fell apart. Then they tracked how its antimatter twin fell apart. If matter and antimatter were perfect mirrors, the 2 should have decayed in the exact same way, at the exact same rate. But they didn't. The team sifted through years of collisions, comparing the particle to its antimatter twin over and over, and a gap emerged. The matter version and the antimatter version decayed at slightly different rates. The mirror was cracked. For the first time in history, scientists watched this everyday class of matter and its antimatter counterpart behave differently, with enough certainty to call it a true discovery. This was a genuine first. The crack in the mirror was finally caught in the kind of particle that builds the visible universe, the family that includes the protons and neutrons in every atom in your body. It was the strongest sign yet that nature really does play favorites, leaning slightly toward matter. And yet, even this triumph carried a frustrating surprise. The scientists measured the crack. They confirmed it was real. But when they checked how big it was, the crack was far too small to explain the entire survival story of the universe. The tiny advantage it gave matter was real, but it wasn't nearly enough to account for the flood of all the matter we see around us. So the deepest part of the mystery is still wide open. The universe clearly survived its death sentence. Scientists have now caught it bending one rule, but the bend is too gentle to have finished the job. Something bigger, still hidden, must have given matter a much stronger push. That hunt leads directly to the strangest kind of matter humans have ever made, a type of matter so dangerous and so rare that CERN builds it one fragile speck at a time. And that matter was used to answer one of the most fundamental questions humanity has ever known. If you drop antimatter, which way does it fall? Down or up? For decades, no one knew. And the question was so wild, it sounded like science fiction. Think how strange this is. You've dropped thousands of things in your life. A phone, a spoon, a ball. A phone, a ball. Every single one fell down, pulled by gravity toward the floor. It feels like the most obvious rule in the universe. But antimatter is the exact opposite of matter in so many ways. Its charge is reversed. Its nature is reversed. So scientists had to ask an honest question. What if its gravity is reversed too? What if, when you let go of an atom of antimatter, it floated upward instead of falling down? What if there was such a thing as anti-gravity, and antimatter was the key to it? This was a real scientific question, debated seriously for decades. If antimatter fell up, it would shatter our understanding of gravity, breaking one of the biggest theories in all of science. It might even give a clue as to why antimatter is so scarce. Maybe it was just repelled by everything, pushed away into the void. The idea was thrilling, but it was also completely untested, because no one had ever managed to just drop antimatter and watch. The problem was always the same. To watch something fall under gravity, you have to hold it gently and then let it go. And gravity is an incredibly weak force. A magnet on your fridge easily beats the gravity of the entire planet on a paperclip, so powerful magnetic forces were completely overwhelming the weak pull of gravity. The solution required patience and courage. Scientists built a tall, vertical trap and filled it with anti-hydrogen atoms, held in place by a magnetic grip. Then they did the scary part. They slowly, carefully weakened the magnetic walls at the top and bottom of the trap, turning down the force bit by bit. As the magnetic grip weakened, the only thing left to guide the atoms would be gravity itself. The question was simple. As the atoms escaped, would more of them pop out the top or fall out the bottom? They ran the experiment, weakened the trap, and watched where the anti-hydrogen atoms went as they escaped and annihilated on the walls. About 8 out of every 10 atoms went down. Antimatter fell. It fell toward the ground, the same way your phone falls, the same way everything has always fallen. There was no anti-gravity, no upward floating, no reversed pull. When you drop antimatter, it obeys gravity just like the matter in your own body. This settled a question that had been hanging in the air for almost 100 years. Antimatter falls down. This closed one door on the mystery of the missing antimatter. Whatever wiped almost all the antimatter from the universe, it wasn't some strange reversed gravity. The question of why matter won remains wide open, with just one wild idea crossed off the list. But all of these experiments keep coming back to one place, one focal point, that penguin decay. And at the heart of that decay is a particle that shows up again and again at the center of CERN's strangest puzzles. And that particle keeps acting like it's hiding a secret. Its name is the muon. It is raining down on your head right now, passing right through your body. This particle, which you met briefly inside the penguin decay, is the electron's big cousin. It behaves like a normal electron in almost every way, except it's roughly 200 times heavier. Think of an electron that went to the gym and got massively jacked. The same basic personality, with a lot more weight behind it. Muons are everywhere, even though you never feel them. High above your head, particles from deep space are constantly slamming into the top of the atmosphere. These collisions spray showers of muons that rain down toward the ground at nearly the speed of light. Right now, a few are passing through your body every second. They slide harmlessly through your skin, your bones, and the floor beneath you without a trace. They are ghost-like, coming and going before you can even notice. But the muon has a dramatic quirk. It doesn't last. A muon only survives for about 2/millionths of a second before it decays into lighter particles. Blink, and you've missed the lifetimes of countless muons. It's this fleeting existence that makes scientists love to study them. They are born, live their momentary lives, and decay in a way that the rulebook claims to predict perfectly. Here is where things get interesting. Scientists have a deep belief about the electron and its heavier cousins. They believe these particles should be treated exactly the same by the laws of nature, identical in every way except for their weight. The fancy way of saying this is that the different cousins should be perfectly balanced. An electron and a muon should act like the same particle wearing different sized jackets. But the muon keeps misbehaving. Over the years, the muon has shown up at the center of several of physics's biggest puzzles. Experiments keep finding small hints that the muon isn't behaving exactly as the rulebook demands. It wobbles where it should be steady. It tilts where it should be balanced. None of these hints have ever been strong enough to count as proof on their own, and some have vanished with more data. But the pattern is hard to ignore. Over and over, when something looks strange in the deepest experiments, the muon is somehow involved. And remember our penguin. When that meson fell apart in its strange rule-bending way, 2 of the particles it produced were muons. The muon sits at the very heart of the decay that started this whole mystery. So when scientists saw that deviation, a quiet thought creeps into their minds. What if the key is the muon? What if this heavy cousin feels a force that the electron doesn't? A secret push from a new particle that only it can sense. If this turned out to be true, it would break the rulebook spectacularly. It would mean that nature secretly plays favorites among these particle cousins, treating the muon differently for reasons no one yet understands. The missing pages of physics might be written in the strange behavior of the muon. This possibility is so provocative that when CERN's giant machine first turned on, a frightening rumor spread around the world. People genuinely feared the collider could swallow the entire planet. This really happened. As the machine was preparing to turn on, a wave of fear spread around the globe. Newspapers ran scary headlines. Worried people sent frantic messages. A few even tried to stop the experiment through the courts, filing actual lawsuits to prevent CERN from turning the machine on. Their fear was like the plot of a disaster movie. They believed that smashing particles with so much energy could accidentally create a tiny black hole, a bottomless pit of gravity that would sink to the center of the Earth and slowly devour the planet from the inside out. it's easy to see where the fear came from. The collider was the most powerful machine ever built. It was smashing particles at energies never reached before. The words black hole are terrifying. Put those ideas together and you get a nightmare, a science experiment that ends the world. So scientists faced a serious task. They had to prove, clearly and calmly, that the machine was safe. And the way they did it was truly clever, because the answer was floating above everyone's heads all along. Remember those particles from deep space? The ones that are constantly raining muons down on you? Many of them carry far more energy than anything the collider produces. These natural particles have been slamming into the Earth's atmosphere for billions of years, every day, colliding with more force than the most powerful machine humans could ever build. The upper layers of the sky are endlessly battered by these violent natural collisions, all over the planet, non-stop, long before life existed. If these collisions could create a planet-eating black hole, it would have happened a long time ago. Countless times, billions of years before anyone ever built a collider. The Earth is still here. The Sun is still here. Every star you can see has been bombarded by these natural collisions for its entire life, and not one of them has been swallowed. Nature was already running the experiment at higher energies, endlessly, with zero disasters. This was the knockout argument. The collider isn't doing anything that the universe isn't already doing harmlessly all around us trillions of times. And even in the wild case that the machine could create a microscopic black hole, scientists understood it would be so tiny and so unstable that it would evaporate and vanish in an instant, before it could even touch a single atom. The machine turned on, the world kept spinning, no black hole appeared. The planet was not devoured. The collider has now been running for over 15 years, producing some of the greatest discoveries in science. And the apocalypse never came. The fear, while understandable, was based on a misunderstanding of just how safe the experiment actually was. But that fear reveals something important about this machine. It pushes into a realm so extreme that people genuinely wonder what monsters it might awaken. And while no black holes came out of the collider, the collisions have indeed produced things that until recently, scientists were sure couldn't exist. Strange particles, impossible combinations, building blocks of matter stuck together in ways the rulebook never expected to see. The collider keeps spitting out particles that should never exist according to the old rules. To understand why these are so shocking, you need to remember how matter is normally built. Quarks are the tiny building blocks locked inside protons and neutrons, and for a long time, scientists thought they only came together in two simple ways. 3 quarks could group together to make heavier particles, like a proton, or one quark could pair up with its mirror twin, an antiquark, to make a lighter particle. Threesomes or pairs. Those were the rules. Those were the only combinations anyone had ever seen. For decades, this simple picture held, but then the collider started finding things that broke the pattern. The team running LHCb, our penguin hunters, discovered particles made of 5 quarks stuck together. 5. Scientists call them pentaquarks. And then they found particles made of 4 quarks, tetraquarks. They've even seen heavy new particles filled with rare ingredients, exotic droplets of matter never before seen in nature, born for just a moment in the violence of a collision. These exotic particles don't break the rulebook in the way the penguin might. They actually fit within the broader laws of physics, in corners scientists had never explored before. But they prove something thrilling. The world of the very small is far richer and weirder than anyone imagined. And each of these discoveries teaches scientists more about the strong force, the powerful glue that holds quarks together. But now, it's time to pause and reflect. What do all these discoveries, these strange particles, these broken mirrors and trembling rules mean for us? When we confront the most basic questions of our existence, what are these findings telling us? And now, it's time to pause and reflect. What do all these discoveries, these strange particles, these broken mirrors and trembling rules mean for us? When we confront the most basic questions of our existence, what are these findings telling us? Because what is happening at CERN is not just a puzzle for physicists, it is a profound reflection on what it means to be human. On one side, you have the largest, most invisible component of the universe, and on the other, you have the smallest, most fragile beings who seek it out, understand it, and even build it, us. How can these two truths exist together? This is one of the most fundamental paradoxes of our existence. Let's now dive into this paradox. The vast majority of the universe is missing, and the Collider has been hunting for this invisible culprit for years without ever catching it. Here's the staggering fact. Everything you've ever seen, every star, every planet, every person, every particle in this video, makes up only a tiny slice of what the universe is actually made of. All the normal matter we know, the stuff in the rulebook, accounts for less than 1/5 of the total. The rest is such a profound mystery that scientists have given it a placeholder name because they don't really know what it is. They call the biggest piece dark matter. It's invisible. It doesn't give off light. It doesn't shine. It's nothing your eyes or any telescope can see directly. It's everywhere, passing through every galaxy including our own, and yet it slips through normal matter like a ghost. Right now, dark matter is most likely streaming right through your body and the entire planet without leaving a trace. So if it's invisible and untouchable, how do scientists know it's there? They know because of gravity. Dark matter has weight, and weight pulls. When scientists watch how galaxies spin, the numbers refuse to add up. The galaxies are spinning so fast they should be flying apart, flinging their stars into the void, but they hold together as if some enormous invisible weight is gripping them, holding the stars in place. That invisible grip is dark matter. We can't see it, but we can feel its pull written across the entire sky. There is about 5 times more dark matter than all the normal matter that exists. Think about that. For every one speck of stuff you can see and touch, there is roughly 5 times more of something we have never detected. The universe is made of a component that remains a complete mystery for the most part, and we are the small, visible minority floating within it. This is the tragic truth. We are strangers in our own universe. We cannot see, touch, or feel the vast ocean that surrounds us, holds our galaxies together, and makes our very existence possible. You, me, all of us are living inside a reality that is more than 80% of what exists, and we cannot interact with it on even the most basic level. This is a cosmic loneliness. It's like having a neighbor who is all over your house, but you can never knock on their door. But here comes the beautiful truth. Even though we can't see it, we know it exists. Even though we can't catch it directly, we can measure its effect. And most importantly, we are looking for it. This is why scientists turn to the Collider, hoping to create dark matter and catch it in the act. The idea is bold. If dark matter is made of some unknown particle, maybe a violent enough collision could briefly pop one into existence, just like the Collider conjures up other rare particles. Then scientists could finally study the invisible stuff that rules the cosmos. But catching it is devilishly hard, because the dark matter would slip out of the detectors without a trace. So scientists use a clever trick. They carefully add up all the energy before a collision, then they add up all the energy in the spray of particles afterward. If some energy is missing, if it vanished into a void the detectors can't see, it could mean an invisible particle took that energy and flew away. Hole in the books. A ghost-shaped gap. For years, scientists have been scanning the collisions for that telltale missing energy, and so far, they have found nothing. Collision after collision, the books balance. The invisible particle refuses to show up. Dark matter remains as hidden as ever, taunting the most powerful machine humans have ever built. This silence is a clue in itself, and it deepens the mystery rather than solving it. You are a part of this search. Even though you cannot feel the invisible matter passing through your body every second, you are part of the minds that are searching for it. This is one of the greatest traits of humanity. We believe in what we cannot see, we try to understand what we cannot comprehend, and we build enormous machines to fill the biggest gap that defines our existence. This is a testament not to our powerlessness, but to our power. Now let's look at another paradox. The contrast between the most elusive particles in the universe and the most massive machines we build to catch them. Trillions of ghost particles are passing through your body every second, and the Collider has just caught some of them for the first time in history. These ghosts are called neutrinos, and they are perhaps the most elusive particles in nature. They are unimaginably tiny. They have no electric charge, and they interact with almost nothing. That last part is the key. A neutrino can fly through solid matter as if it were empty air. It can pass right through a planet, through the rock, metal and molten core, and come out the other side without ever hitting a single thing. The numbers are almost unbelievable. Right now, every second, about 100 trillion neutrinos are passing through your body. They pour out of the sun in unimaginable numbers, and they rain down on us day and night, awake or asleep, indoors or out. You feel nothing because almost none of them ever touch you. A neutrino could pass through a wall of solid lead that stretched for light years and still have a good chance of coming out the other side untouched. This is what makes studying neutrinos so frustrating. To detect a particle, it usually has to hit something in your machine. But neutrinos hit almost nothing. They are the ultimate ghosts. They slip through every trap, ignore every wall, and fly past the most sensitive detectors as if they aren't even there. This is the tragic truth. The universe is filled with particles constantly whispering its most fundamental secrets to us, but we are almost completely deaf. Trillions of them pass through our skin, our bones, our hearts every second, and we are almost entirely unaware of their existence. It's like being blind and deaf in a room filled with information. They are everywhere, but for us, they are almost nowhere. But that small team at CERN changed that with a brilliant idea. For a long time, scientists assumed the collider would never catch them. Yes, the collisions were definitely producing neutrinos, but those neutrinos would just stream into the ground undetected, lost forever. Then a small team had a brilliant idea. They built a special detector and tucked it away in a tunnel far from one of the collision points, perfectly positioned in the path of the neutrinos streaming out of the collisions. They filled it with dense material, offering as many opportunities as possible for the ghost neutrinos to finally hit something. Then they waited, hoping that out of the countless neutrinos passing through, just a few would actually strike the detector and reveal themselves. And it worked. For the first time in history, scientists detected neutrinos created inside a particle collider. The ghosts born in the violence of the collisions were caught, red-handed. It was a true first. It opened up a brand new window onto these slippery particles at energies they had never been studied at before. You are part of this moment. Even though you don't feel those trillions of neutrinos, you are part of the collective intelligence of humanity that managed to catch them. It's like building a giant ear in a silent room just to be able to hear the faintest whisper, and that whisper might carry clues to the biggest secrets, like why the universe prefers matter over antimatter. This is a story not about our smallness, but about our persistence. Where it's easy to ignore, we choose to listen. But amidst these giant concepts and cosmic mysteries, there is a more personal, more direct question. How do these machines, these discoveries, affect our daily lives? And the answer to that question is hidden in the most unexpected places. Because the most explosive substance in the universe is sitting quietly inside hospital machines, helping doctors see inside living bodies. This seems impossible after everything you've just learned. Antimatter annihilates on contact. It's rare, precious, and dangerous. So how could it possibly be used in a hospital near actual patients? The answer reveals just how clever humans have become at taming the impossible. The machine is called a positron emission tomography scanner, but almost everyone just calls it a PET scan. If you've known anyone who needed to look for a hidden problem deep inside their body, a tumor, a strange spot, something that couldn't be seen from the outside, there's a good chance this machine was involved, and that machine runs on antimatter. Here's how it works in a simplified way. Doctors give the patient a tiny, harmless amount of a special substance that naturally emits positrons, the antimatter twin of the electron. The patient barely notices. Inside the body, these positrons travel a microscopic distance before they encounter the ordinary electrons, the matter that make up every cell. And you already know what happens when matter meets antimatter. They annihilate. Each little annihilation releases a precise burst of energy, 2 little flashes of light that shoot off in exactly opposite directions. The scanner is a ring built to catch those flashes. By recording where the flashes of light came from, the machine maps out exactly where all those annihilations are happening inside the body. Cancer cells, for example, are hungry and active, so they absorb more of the substance and produce more flashes. They light up on the scan like glowing spots, revealing themselves even if they are buried too deep for any eye to ever see. Here is another paradox for you: the contrast between the greatest destruction and the most delicate healing. On one side, you have the universe's most efficient mechanism of destruction, where an amount the size of a paperclip could rival a major nuclear weapon. This is that absolute end when matter and antimatter meet, where everything is converted to pure energy, leaving nothing behind. This is a force that could level cities, that could unleash the greatest power imaginable. The tragic truth is that the universe itself was born on the brink of this destruction. Everything should have been annihilated instantly, leaving only a cold light. This is the terrifying potential that underlies our very existence. But then we turn to the beautiful truth. That same annihilation, the same destruction that makes antimatter the most dangerous fuel, becomes a gentle searchlight inside a human body. The destruction is so small, so controlled, that it harms nothing, and instead saves lives by showing doctors exactly where to look. The patient feels nothing. The flashes are invisible. The machine just reads the light and draws a map. You are part of this paradox. Your body is made of the matter that shouldn't exist. And one day, that same principle of annihilation could be your greatest weapon against one of the most invisible enemies. This is a testament to our ability to take the wildest force of nature and use it for the most compassionate purposes. This is the quiet secret of science. The research can seem useless, even crazy. Why study antimatter? Why smash particles for fun? Then years later, that wild experiment becomes an everyday tool that saves your grandmother. The collider may be hunting the deepest mysteries of reality, but its discoveries keep trickling down into the hospitals, the computers, and the technology you already use. But what about our relationship with knowledge itself? On one side, we have a rulebook that has stood unshaken for 50 years, revealing how the universe works on its most fundamental level. On the other, we have a single stubborn data point that has been growing for a decade, whispering that the rulebook might be wrong. How do we live in this tension between certainty and doubt? This is another deep contrast at the heart of science, and indeed, of being human. The Standard Model is the most successful idea in history. Nothing else comes close. Its prophecies have been proven true time and time again. Its predictions have been tested by our most sensitive machines and have come out correct every time. It is the solid foundation upon which we have built our civilization. We trust it. We rely on it. It promises order and predictability in a universe that can seem like chaos. The tragic truth is that clinging to this certainty can be dangerous. If we hold on to a theory so tightly that we ignore the evidence that suggests it might be wrong, then we stop doing science and start practicing dogma. The story of the 750 GeV ghost reminds us of this. Wholes of brilliant people got so caught up in something that looked real that it was painful to admit it was a mirage. It's a humbling reminder that even the smartest brains can fool themselves. But this is why the beautiful truth emerges. Science is built on doubt. Its greatest strength is not its infallibility, but its willingness to admit it can be wrong. This is why the 5 Sigma rule exists. It is a brutal standard that scientists impose on themselves to protect themselves from jumping to conclusions. It is to say that a 1 in 16,000 chance is not good enough, because the cost of being wrong is far greater than the thrill of being right. This is why the penguin deviation is not a crisis, but an opportunity. It is a sign that the system is working. The scientists are not celebrating, they are demanding proof, and you are part of this process. Perhaps in some area of your life you have believed something with certainty, only to be confronted with evidence that proved you wrong. It is an uncomfortable feeling, but it is also the only way to grow. Certainty offers comfort, but doubt offers progress. These philosophical reflections show that our quest to understand the universe is not just about numbers and equations. It is also about understanding our own place, our own limitations, and our own potential. But beyond all these internal journeys, there is a more practical, more urgent question. What do we do with this knowledge? How will these giant machines, these astonishing discoveries, shape the future of humanity? And that question brings us to a deeper layer, our relationship with knowledge itself. These massive machines are not just generating data about the universe, they are forcing us to confront the workings of our own minds, the nature of our curiosity, and the responsibility that comes with knowledge itself. Because on one side, you have a planetary-scale collaboration, bringing together tens of thousands of scientists, dozens of countries, and billions of dollars. On the other, you have the focus of all this massive effort, the behavior of a single particle, so small that millions of them could fit on the period at the end of a sentence. This incredible contrast in scales reveals humanity's greatest strength and, perhaps, its most poignant tragedy, the boundlessness of our desire to understand and the smallness of our physical existence. Let's now consider this massive collaborative mechanism. The collider produces so much data that storing it would crush every laptop on the planet. This is why scientists built a brain that spans the globe. You already know that collisions come fast. Inside the machine, collisions happen about 40 million times per second, and each one sprays out a storm of particles that the detectors record in fine detail. If scientists tried to save every piece of every collision, the flood of information would be so vast it would fill the world's hard drives in an instant and keep going. There is no way to save it all. So the first thing the machine does is throw most of it away. Lightning-fast computers sit right next to the detectors and make brutal, instantaneous choices, throwing out the boring, ordinary collisions and keeping only the rare, interesting ones. They throw away almost everything, keeping only a tiny fraction that might contain something worth studying. But even after throwing away that vast majority, what's left is still staggering. Every year, the collider records a mountain of data so large that no single computer could ever process it. This is where the genius comes in. A single machine couldn't handle it all, so scientists never tried to build one. Instead, they connected computers all over the planet into a giant shared brain. When a collision is recorded at CERN, its data can be instantly shot around the world, sent to powerful computer centers scattered across dozens of countries on multiple continents. Thousands of machines work on the problem at once, each one taking a piece, all of them stitched into a single worldwide network of computing power. The tragic truth is that to uncover the most fundamental secrets of the universe, we need to pool the entire collective intelligence and technological might of humanity just to even comprehend the data produced by a single experiment. It is a testament to how vast the problem is and how limited we are. We have to build a planet-sized ear just to hear a particle's whisper, but at the same time, this reveals humanity's most beautiful aspect. This planet-wide network is one of the largest computing systems humanity has ever built, and it was built for one purpose: to understand what happens when particles collide. And it has to be this big because the discoveries are buried so deep. Remember our penguin? To find that deviation, scientists had to sift through roughly 650 billion particle decays, looking for that tiny sprinkle of rare events that mattered. That kind of needle-in-a-haystack search is only possible because of this global brain. Without it, the data would just pile up, unread and undiscovered, its secrets locked away forever. You are part of this global brain. Even if you are not physically connected to those computers, you are part of the collective human project that made their existence possible, that asks these kinds of questions and seeks the answers. This is a testament to how we can come together to overcome our individual limitations. We can focus on a single common goal across language, culture, and borders to understand. This is our greatest strength. Alone, we cannot hear the whisper, but together, we can catch even the quietest signals. And what about our dreams for the future? On one side, we have the machine we have today, 17 miles long, the most powerful humanity has ever built. On the other, we have the dream of scientists for a machine so vast it will make even that one look small. What does this say about the insatiable nature of our curiosity? Scientists are already planning a machine so big it would dwarf today's giant collider. Think about that for a moment. The current machine is one of the largest objects humans have ever made. A ring nearly 17 miles around, stretching under 2 countries, cryogenically cold, and unbelievably powerful. It found the famous mass-giving particle. It caught the cracked mirror between matter and antimatter. It noticed the penguin deviation that could rewrite everything. And yet scientists look at all that and say, we need more. Why? Because the deepest questions require even more power. To create heavier particles, to peer even deeper into the wreckage of a collision, to recreate moments even closer to the Big Bang, you need to smash particles together harder than ever before. And to smash them harder, you need a bigger ring. A bigger loop allows the particles to accumulate more speed and energy before they collide, opening doors that the current machine can't reach. The tragic truth is that no matter how big we build, there will always be a horizon we cannot reach. Every answer breeds new questions. Every discovered land reveals a larger ocean beyond. There is no end to knowledge, and this is both thrilling and a little melancholic. We must face the fact that we can never say, "We know everything." But this pursuit itself is what gives our existence meaning. Scientists have drawn up a dream machine, a future collider that would dwarf the one today. The proposed ring would be nearly 57 miles around, more than 3 times the size of today's tunnel. Imagine a circle so vast it would encircle an entire region, buried deep underground. A loop so long it would take hours to walk across. It would be the most ambitious scientific instrument ever attempted. A cathedral built to worship the smallest things in existence. A machine like that could chase the very mysteries this video has revolved around. It could hunt for that hidden particle pulling on our penguin, the one too heavy for the current collider to create directly. It could search harder for dark matter, the invisible majority that haunts every galaxy. It could study the cracked mirror between matter and antimatter with a far greater precision. And you are part of this dream. That machine may not be built in your lifetime, but you are part of the human spirit that dreams it up, that plans it, and that works to make it possible. The current collider was once just a dream, met with skepticism and debate, and it has reshaped our understanding of reality. The next machine could do the same, revealing wonders we cannot yet even imagine. This is the story of our species. We stand at the edge of what we know, look into the darkness, and begin designing the tool that will let us see just a little bit further. This quest for knowledge, these great machines, this global collaboration, all of it points to a single fundamental truth. But to understand what that truth is, we need to approach the end of the story, the moment where everything comes together. And this fundamental truth is the deepest paradox at the heart of this entire journey, the relationship between the answers themselves and the act of seeking them. Because on one side, there is a concrete, ultimate truth that scientists are chasing. Whether the rulebook is correct, whether the penguin deviation is a real discovery or a ghost, a definite, testable, universal answer to how the universe works. On the other, there is the fact that the path to that answer, the search itself, the uncertainty, the doubt, and the curiosity is what truly defines who we are as humans. How can these two ideas, the desire for certainty and the ability to live with uncertainty, exist together? This is the spirit of science, and it is our story. Consider for a moment what will ultimately solve the penguin mystery. Data. More data. The answer is hiding in a massive trove of data that physicists already have, but haven't finished analyzing. This is the most thrilling fact in this story. When the scientists revealed the 4 sigma deviation, they were working with data collected during a previous run of the collider. Since then, the machine has kept running. It never stopped smashing protons, recording collisions, feeding its global brain. And in that time, scientists have collected far more data on these exact penguin decays. We are talking about roughly 3 times as many mesons as the original study was based on. 3 times more evidence, already captured, waiting. The tragic truth is that the answer to one of the deepest secrets of the universe might be sitting on a hard drive right now. But getting to that answer requires months, perhaps years, of meticulous, grueling, and often tedious work. The truth is there, but the path to it is long and arduous. It's like having a treasure chest at our fingertips, but having to navigate a vast labyrinth to find the key that opens it. But this very situation reveals the most beautiful and hopeful aspect of science. The answer is already there. The universe has already shown its hand. We just need to finish reading the cards. This is the strange agony of the situation. The truth exists. It's recorded. It's real. Somewhere in that ocean of new collisions, the penguin either continued its strange behavior or it fell back in line. And no one knows which one yet. The outcome is fixed. Only our knowledge is incomplete, and it doesn't stop there. The collider is preparing for a massive upgrade that will pour out data at a rate that will make today's flood look like a trickle. Scientists are preparing for a version of the machine so powerful it will collect many times more collisions than have ever been collected before. This is the most concrete expression of our species' unending curiosity. When we find an answer, we build a bigger tool to dig deeper. You are part of this anticipation. You don't know the outcome, but you know the question has been asked, and you know the answer is on its way. It is that tense, exciting wait before turning the final page of a story. Uncertainty can be uncomfortable, but it is also that magical moment when all possibilities are alive. So what if it all turns out to be a ghost? What if the penguin deviation, just like the 750 GeV bump, vanishes with more data? Is that a failure? On one side, there is the fact that a decade of hope, thousands of hours of work, hundreds of papers, and countless debates would have turned into nothing. The dream of finding that first crack in the rulebook would be postponed once again. This is a sad moment. It is always difficult to realize you have been chasing a mirage. The tragic truth is that nature does not give up its secrets easily. It often leads us down false paths, it tests us, and it hides its most precious truths in the deepest places. But even this journey is a victory. If the deviation disappears, it does not mean that science has failed. It means that science has worked exactly as it should, demanding proof before belief, refusing to be fooled. Every wrong path fills in another part of the map. We learn where not to go. It shows us once again just how unbreakable the rulebook is, how robust the laws of nature are. You are part of this process. You are the heir to a mindset that understands that the falsification of a hypothesis can be as valuable as a discovery, because it means loving the truth more than your desire. It means embracing the possibility of being wrong more than the comfort of fooling yourself. And that is one of humanity's noblest quests. This entire philosophical journey brings us back to where we started, to that giant ring beneath the border of Switzerland and France, to a strange deviation, to a crack seen by two machines, to an ocean of data waiting for an answer, to the fact that the universe should not exist, but it does, and that we are small, curious creatures within that existence, searching for meaning. This journey has shown us that our quest to understand the universe is not just a journey outward, to the stars and particles, but also a journey inward, to our own limitations, our potential, and the deepest paradoxes of our existence. It is now time to bring this vast picture together. What do these fragmented clues, these trembling rules, and these stubborn ghosts ultimately tell us? What will be the end of the story? And so, the end of the story is actually a beginning. On this journey, we've descended from a 17-mile giant ring beneath the border of France and Switzerland to the world of particles a trillionth of a time smaller than an atom. We've seen how a rulebook that has not been wrong for 50 years is trembling in the face of a stubborn deviation that has been growing for a decade. We've understood why the universe is not empty, thanks to that broken mirror between matter and antimatter. And we've realized that this entire quest is actually a journey to understand our own limitations, our curiosity, and our courage in the face of uncertainty. We now know that that penguin decay is not just a particle falling apart incorrectly. It is a question we are asking of our most fundamental assumptions. That 4 sigma deviation could be a coincidence that happens once in 16,000 tries, or it could be the first whisper of the greatest discovery in history. And we are the generation that gets to hear that whisper. You're at the very center of this story. Every single atom that makes up your body comes from that one particle that survived that cosmic battle billions of years ago, and your mind is part of that incredible human project that can build planet-sized machines to solve the secrets of that particle. If this journey has made you feel how strange the universe is and how precious our quest to understand it is, let's continue this conversation in the comments, like, and subscribe, because this story doesn't end here. Everything we've seen is the result of an event that determined the fate of everything in the first moments after the universe's birth, and that first moment was far more violent than we could ever imagine. In this video, we've examined the events after the birth of the universe. But I didn't tell you something. In less than a trillionth of a second of the universe's first second, All the laws of physics we know were meaningless. In that moment, the universe expanded from a point smaller than a grain of sand to an area larger than a galaxy, at an unimaginable speed. This was cosmic inflation. In our next journey, we will dive into that moment. Are you ready?